This is the second of a three-part video series covering section 6.3 on Taylor and Maclaurin series in the OpenStax Calculus book, Volume 2. In the first video, we talked about what a Taylor and Maclaurin polynomial was and talked about how these can be used to approximate various functions. In particular, we can approximate transcendental functions, which may or may not be easy to compute without a calculator or computer handy. Keep in mind that Taylor and Maclaurin polynomials and the series that are based on those polynomials are one of the common ways of actually programming different transcendental functions into computers. While most computers now use more sophisticated series rather than Taylor and Maclaurin series, the basic method is the same. They are used to compute the values for transcendental functions such as exponentials, natural logs, sine, and so forth to a high degree of accuracy by adding and subtracting terms of an infinite polynomial. However, since they can't do the infinite polynomial, they take the Taylor or Maclaurin polynomial type object and use a finite number of terms. Since computers are very fast at performing calculations like this, we can get the answer very quickly. Let's talk about the idea of what a Taylor or Maclaurin series is and how it is different from a Taylor or Maclaurin polynomial. Below, you will see the definition for a Taylor and Maclaurin series. In a Taylor or Maclaurin polynomial, we have the sum and difference of a finite number of terms, usually up to n is the way that we write it. Now, in the one that I did for you in the previous video, I used k for the index of summation for the series so that I could use n as the upper limit of the summation for the Taylor and Maclaurin polynomials. When you allow the number of derivatives matched on the polynomial to go to infinity, you end up with what's called a Taylor series. If you center that series at 0, then we'll call it, of course, a Maclaurin series. This implies that you must be able to take the derivative of all orders at that value where you're centering that particular function, which must mean that it has infinitely many derivatives. If that's the case, then we can define the Taylor series for the function by this expression you see here. You'll notice that the first part is again the formula for getting the coefficient, the kth derivative at the center divided by k factorial. Then it's multiplied by the binomial factor x minus the center raised to the kth power. The book tends to use n, but I will probably continue to use k as I don't want to confuse you and use different notation in different videos. You'll notice when you expand this out that it looks just like what we did yesterday for the Taylor and Maclaurin polynomials, except that it continues forever. The Taylor and Maclaurin polynomials stopped after the nth one. We have a couple of questions that we'll need to figure out while we're working with these. One of the first questions is, how will we know whether or not the Taylor series converges? And second, if it does converge, how will we know what the Taylor series converges to? It is a crazy idea, but the truth is you can use one function to develop the Taylor series, but it can converge to a totally different function. This can be a problem. So we need to know when it converges and also what it converges to. Does it converge to the same function that generated the series or to something totally different? Because the Taylor series are power series, they are unique for each function used to generate them and each value of the center. However, there could be a couple of different ways to derive the different Taylor series, but they are unique in their format. In order to know where the Taylor series converges and whether or not it converges, we'll have to look at the sequence of partial sums. However, Each partial sum is itself simply a Taylor polynomial. So the partial sums become the Taylor polynomials that we studied in the first video. Again, the only difference between the Taylor and Maclaurin series and Taylor and Maclaurin polynomials is whether or not the center is the value a equals 0. Recall from the previous section in the textbook that if we have a power series representation at a particular center value x equal a, then that power series representation is unique. That means that the power series you derived must be the Taylor series. In other words, it is a unique function. If the function f has a power series at a and it converges to the same function on some open interval containing the center, then that power series must be, in fact, the Taylor series for the function at a. Sometimes you don't recognize that it is the same series, but in fact it is, and there must be some method algebraically to convert one into the other. Let's take a quick look at example 5, which is finding the Maclaurin series for the function sine x. We worked with sine x in the previous video, but in that video we were only looking for the Maclaurin polynomial. Now we want to take a look and see what we need to do in order to come up with the Maclaurin series that never stops and continues forever and ever. The beginning steps of trying to find a Maclaurin or a Taylor series for a function are exactly the same as finding the Taylor or Maclaurin polynomial for the same function at the same center. Since this says up at the top that we want a Maclaurin series, remember that that means that the center A must be 0. Otherwise, they would call it a Taylor series and give you the center separately. What I mean by the steps are the same is that we have to go through and we have to compute the nth derivative for the function, and then we need to plug in the center. Again, we'll want to do probably about 4, maybe 5 different differentiations because we will have to try to find a pattern so that we can rewrite the Maclaurin or Taylor series in a summation formula. If you only do 1 or 2 derivatives, it may not be enough to see the pattern starting to develop. My advice is, when doing the derivatives, do not multiply out the constants. Leave them factored. In other words, if it has a 2 times a 3, don't write it as 6. Leave it as 2 times 3, or 2.3. Let's run through and find, say, the first 4 derivatives for the Maclaurin series sine x. Remember that the 0th one is not, in fact, a derivative at all. The 0th derivative is just the function itself, and ours is sine. The first derivative of sine is cosine. The second derivative of cosine, or of sine, which is the derivative of cosine, would be negative sine. Third derivative would be negative cosine, and let's do one more. The fourth derivative, which would give me back around to sine again. Now I'm going to plug in the center into each one of these, and then I'm going to look and write them down to see if I have a pattern. If I can't detect the pattern, then I'll need to evaluate more derivatives until I can find it. That's why you'll see that there are still a couple of blank lines in the chart. So the next step, of course, is to evaluate it at the center. Our center is 0, since it's a Maclaurin series. That means I'm evaluating the sine of 0, which is 0. Remember that both cosine and sine will alternate with zeros, which makes them both easier and harder since you'll have to compute more derivatives to find the pattern. The cosine of 0 is 1. The second derivative at 0, which is negative sine of 0, is also 0. The third derivative at 0, which is negative cosine of 0, would be -1. But the fourth derivative is again going to take us right back around to the sign of 0 again. We know that this is a repeating pattern because it's sine. Cosine also has a repeating pattern every 4. Let's write down at least the first few terms here of this infinite polynomial. Our signs are repeating 0, 1, 0, -1, 0, 1, 0, -1. You may want to write that pattern down so you don't have to keep scrolling up and down. 0, 1, 0, -1. Then back to 0, 1, 0, -1. Remember that the formula involves two parts. One, having to compute the coefficient, which is found by taking the kth derivative of the function with the center plugged in, which gives you a number from column 2, divided by the same value as the derivative you took with a factorial behind it. That gives us the coefficient. Then we multiply it by the binomial factor x minus the center raised to the kth power. Since we have a Maclaurin series and the center is 0, our x minus a's will devolve to x to the k since a is 0. Let's compute the first few. This means if I'm trying to find the infinite series that I should have c sub 0 x to the 0 plus c1 x to the 1 plus c2 x squared plus c3 x cubed plus c4 x to the 4th plus ... The ... represents that this is a series that never ends. It's an infinite polynomial. Now let's compute the coefficients. C sub 0 is the 0th derivative of the function at the center, which we found to be 0. 0 divided by 0 factorial. X to the 0 is the number 1, but of course that generates a 0 due to the 0 in the numerator of the coefficient part. Now let's look at the second term here, c1x to the first. The first derivative at the center had value 1. We divide by 1 factorial times x, which gives us a plus x. The second derivative at the center was also 0. That's that 0 right there. That will give me a 0 on top. 2 factorial times x squared is going to be another 0. The next term, however, is c3, and this one had a -1 as the third derivative at 0. So this will give me a -1 over 3 factorial x cubed. Again, do not multiply out the 3 factorial, but leave it in its current form. 1 over 3 factorial x cubed. C4 would also likewise disappear because the next number in the pattern is 0. It doesn't really look like I have enough to know what the next pattern is going to be, so I'm going to extend it by using my knowledge of what the numerator has to be to continue writing the pattern. This will be 0 over 4 factorial x to the 4th, and then the next number, since this is this one here, this is the 0th, the 1st, the 2nd, the 3rd, the 4th, the 5th. This should have a 1 on top, which would give me a plus 1 over, and then it should be 5 factorial x to the 5th, then another 0, and then the 7th will be a -1 over 7 factorial x to the 7th plus ... The next thing I want to do is put down the parts that are not 0. That means I have a plus 1 over 5 factorial x to the 5th and a -1 over 7 factorial x to the 7th. Let's clean this up and create a little bit more space so we can see what we have. Recopying this at the top of the next page, this means that my infinite polynomial starts with x, then has 1 over 3 factorial x cubed, plus 1 over 5 factorial x to the 5th minus 1 over 7 factorial x to the 7th, and then it keeps going. This should be enough for us to predict what the pattern's going to be. Let's see if we can come up with a pattern. Remember that when you're looking at a pattern, it's typically the second, third, and fourth terms that are the most useful. Then you want to back up your pattern and make sure it matches the first term. We want to write this as an infinite sum. I'm going to use k for the lower limit of, or the index of summation, and it's going to go to infinity. You'll notice I've left a blank where the lower index of summation would be because I don't know what number to start with yet. Looking at these, I can see I have alternating signs, positive, negative, positive, negative. That means I have a -1 to some power, which I'm going to leave as a question mark for right now. Then I need to have a 1 divided by an odd number with a factorial. There are two ways to get odd numbers. Even numbers can always be gotten by multiplying the subscript by 2. Odd numbers then are directly in front, 2k minus 1, or directly after it, 2k plus 1. Whichever one you choose will also help you to determine what this lower index of summation is. You can use either one. I'm going to use 2k minus 1 for mine. So it looks to me like I should be dividing by an odd number, 2k minus 1, with a factorial on it. I also should take x to exactly the same power, so the power on x should also be 2k minus 1, since these powers match the factorial. The numerators are always 1s. Let's suppose that I started with 1. If I start with 1, then 2 times 1 is 2. 2 minus 1 is 1. So I get 1 over 1 factorial, which is 1. This would multiply it by x to the first. That would generate the x here. Now I need to fix the sign that goes on the -1 so it starts positive. The problem is if I use k, this will be negative. I can use the same trick here to change the signs. I need the first one to be positive, so I could add 1 or subtract 1 to my current k value. I don't want it to always be even or odd since I want it to change back and forth. So if I add 1, that will guarantee that the first one is even, the second one's odd, then even, then odd, and so on. This will generate the pattern that I'm looking for. You could have started at a different value here, but then you would need to adjust your indices here. You could also have used k minus 1 here, and that would also generate exactly the same sequence. Your answers here are not necessarily unique. This is our example of what it should look like in order to get sine of x centered at 0 written as an infinite Maclaurin series. Now the question that we come to now is, when does this converge and when does it not converge? To determine whether or not it converges, remember you have two strategies. One strategy is to try to get everything that depends on the subscript or the index of summation into parentheses with a power related to the index of summation outside. Unfortunately, we have 2k minus 1 here. It is not being raised to the k power, but it does depend on k because I have k there. That means I cannot write it in a purely geometric form. Since purely geometric form is off limits, my only option is to use the ratio test. The ratio test will let me get some kind of boundary on the x variable that will require it to converge. Let's go ahead and find that now. So now I'm going to use the ratio test. Let me change colors. So I'm going to use the ratio test. to find the interval and radius of convergence. Remember that when you apply the ratio test, you're taking a limit as the subscript goes to infinity of the ratio of the n plus first term over the nth term, or in our case, the k plus first term over the kth term. So we have rho is equal to a sub k plus 1 over a sub k. A way to reduce some of the algebra is to think of this as ak plus 1 times 1 over a sub k, where you take the reciprocal of a sub k and multiply by it. Remember that this is actually the Greek letter rho, and we need this to be either 0 or less than 1 to get it to converge. Let's now write down our formula for the summation. Remember up here that when you're looking at these, the value that you consider to be a sub k does not include the negative behavior that makes it alternate. The reason is because when you put it in the absolute values, it disappears anyway. So what we're looking at for our a sub k is, and I can write them in one fraction, as 2x to the 2k minus 1 over the quantity 2k minus 1, the whole thing factorial. That is my a sub k. So I have now, if I can remember that long enough, I've got x to the 2k minus 1. So that's x to the 2, open up a hole, minus 1 over, and what was the other part? 2k minus 1 factorial. 2 times something minus 1, that whole thing factorial. You'll notice that I've left empty parentheses for where the k plus 1 should go. This is an easier way of doing it so that you don't make an arithmetic mistake. I see all the time that students make arithmetic mistakes because they try to do too many steps at once. My advice is don't do it. Now we need to take the reciprocal of a sub k, which would be this upside down, and multiply by it. So this will give me 2k minus 1 factorial over x to the 2k minus 1. All of that is inside the absolute values. The next thing you should do is simplify the arithmetic here. If you've left yourself enough space, you can work directly above or below. In my case, I get 2k plus 2 minus 1, which is 2k plus 1. That means that this is also 2k plus 1 quantity factorial. Now I'm going to rewrite it below so that I can continue to simplify it. We'll have to add more space since these examples usually take quite a bit of room. In the next line, we need to clean up the algebra a little bit. One of the things that will simplify it is to get the corresponding parts written one directly above the other. In other words, let's get this x to the 2k plus 1 directly over the x to the 2k minus 1, since they're both x to a power. This gives me x to the 2k plus 1 over x to the 2k minus 1. You're allowed to do this since you have multiplication in the numerator and denominator, and multiplication is, of course, commutative and associative. So you can reorder it any way you want. Let's now take a look at the next part. We need to get the factorials directly over each other. So I'm going to write this as times. In the numerator, I have 2k minus 1 factorial, and in the denominator, I have 2k plus 1 factorial. There is a rule for exponents that says if the bases are the same and ours are both x, then you subtract the powers, the numerator power minus the denominator power, when they're being divided. That will be the next step to simplify that part. So on the next page, rho is still equal to x to the 2k plus 1 minus in parentheses 2k minus 1. If I simplify that, and I will in a moment, you'll see that the 2k's are going to cancel, but the 1's will double. The second part, in order to simplify it, I need to take the larger factorial, 2k plus 1 quantity factorial, and bring it down until we get to the level of 2k minus 1 quantity factorial. That means that in the denominator, I need to write the 2k plus 1 factorial as 2k plus 1, subtract 1 to get 2k, and subtract 1 more to get 2k minus 1 factorial. In the numerator, I have another 2k minus 1 factorial. Since those factorials are identical, they will cancel, but the 2k plus 1 binomial factor and the 2k are left behind. Again, if you've left enough room, then you should be able to work out some of this arithmetic below or above, which gives me 2k plus 1 minus 2k plus 1, which is 2. Continuing on with the algebra, we can now reduce rho to being the absolute value of x squared times 1 over 2k plus 1 times 2k. The x does, oops, I have lost my limits. So up here, I should have limit on all of these. My bad. I knew something was missing, and this is as k goes to infinity. Oops, not x, k is going to infinity. Because the x does not depend on k, it is, as far as the limit is concerned, a constant. That means I can take the x squared out of the limit and pull it to the front. If the power on the x depended on k, I would not be able to do that. But because the x and the 2 are independent of k, I can pull it out. This will let me simplify the limit as x squared times the limit as k approaches infinity of 1 over 2k plus 1 times 2k. Now, the second part of this, where the limit is definitely going to go to 0, since this becomes a quadratic equation if you multiply it out, but the top is a constant. As k goes to infinity, the quadratic goes to infinity, but 1 stays at 1. That gives us the form of 1 over infinity, which tells us that it must be going to 0. Now, this is an important result. You'll notice two things. One, when I brought the x squared out, I didn't put it in absolute value. Normally you should, but a squared thing can never be negative, so I didn't have to worry about it. This also matters because x squared times 0 is going to be 0 no matter what the value of x is. This tells me that rho is 0 for all x values. What that tells me is that it doesn't matter what x is, this converges for all x values. There's no restriction on what I can put in for x that will still make this converge to the value of sine of x. That means I can plug any value I want into this infinite polynomial, and I will get the precise value of the sine function right there. So this converges for all values. This means our radius of convergence is infinity. And it means that our interval of convergence is from negative infinity to positive infinity. This means that that particular Taylor series, that Maclaurin series that we found for sine, will give us the value of sine for any number we want. This is a hugely important result since we can now approximate any value of sine to a very, very high degree of accuracy using nothing more than addition, subtraction, multiplication, division, and powers. Those are things that computers can do extremely quickly. And this is very similar to the way that all modern calculators and computers actually do compute sine. Let's move on to the next example. You'll notice that I've kept the numbers a little bit different, as if all of the videos were one video. But again, because this information is so important and so vital that you understand it, I did break it up into multiple videos. Let's now find the Taylor series for sine of x, the same one we did before, but this time we're going to center it at pi. Now, we know that the pattern for the nth derivative will not change, but we know that when you plug in the center, it could change. Let's see if it does change or not. Since we've done sine multiple times now, you should be able to quickly write down what the nth derivative for sine is. The nth derivative is just the original function unchanged. First derivative, cosine. Second derivative, negative sine. Third derivative, negative cosine. Fourth derivative, back to sine again. We'll do the next two just for fun. Fifth derivative, back to cosine. Sixth derivative, back to negative sine. The next step, of course, is to plug in the center, but this time our center is pi. If a equals pi, then I need to plug pi into each of those derivatives. The 0th derivative isn't actually a derivative, it's just the function. So I can now write sine of pi, which is 0. Cosine of pi is negative 1. Notice that while the first term gave us 0 again, the second did not give us 1 as we found previously, but instead gave us negative 1. So while they're similar, they're not exactly the same. Negative sine of pi is 0. Negative cosine of pi would be a double negative, so it's a positive 1. And then it repeats again. 0, negative 1, 0, 1. If we wanted to continue the pattern. So this time our pattern is 0, negative 1, 0, 1. And you'll see that I've grouped them here in groups of 4 to emphasize that it does repeat every 4. The next step, of course, is to write down some of the terms until we can see the pattern developing and until we think we can write the pattern as an infinite sum inside the summation notation. I'm going to skip the 0 term since I know that any derivative that is 0 in the numerator is going to disappear. This means this one is the 0th one, this is the first, this is the second, this is the third. Make sure that you do get the numbers correct and that you don't mistake the first 0 as the first derivative. It's not, it was the 0th derivative. When we write out the terms, remember that we should have C0 times x minus the center, which is pi to the 0, plus C1 x minus pi to the first, plus C2 x minus pi squared, plus C3 x minus pi cubed, and so forth. You'll notice now that the C sub 0 is 0, and that's going to make that term disappear. The second is also 0, so it disappears. In fact, all the even terms disappear and only the odds are left. That's going to let me rewrite it then as C1 x minus pi. C1 is the first derivative, which was negative 1, over 1 factorial times x minus pi to the first. C3 The third derivative at pi was a positive 1, so I get 1 over 3 factorial x minus pi to the third. The next term that would not be 0 would be the fifth one here. The fifth one also had a negative 1 for the fifth derivative at pi, and we'll divide by 5 factorial and raise x minus pi to the fifth power. The last one we have written is the seventh, but it would be a positive 1 over 7 factorial x minus pi to the seventh. However, the Taylor polynomial or the Taylor series does not stop there. It goes forever. A Taylor polynomial would stop. Let's see if we can look at that and come up with a pattern for that particular formula. It looks to me as though I could write it as the sum. I definitely have alternating signs, so I'll have a negative 1 to some power. If I presume that I'm going to start when x is, or k is 1, I know I'm going to be multiplying by x minus pi to a power. I don't know what the power is, and I know I need some kind of odd number factorial in the denominator. As I did before, I'm going to use 2k minus 1 for my factorial. That way, when k is 1, I should end up with 2k, which would be a 2, minus 1 is 1 factorial. That would give me this 1 factorial. The power on the x minus pi should match that. So I think that I should use 2k minus 1 for the power on x minus pi again. This shouldn't be a surprise, since the only real difference between this example and the previous one is where the center is and the values of the derivatives. The next thing I need to do, now that that seems to be working, so when k is 1, this will generate the 1, and this will have power 1. When k is 2, 2 times 2 is 4, minus 1 is 3. So the next denominator will be 3, and the next power will be 3. Now I need to fix the alternating sign behavior. I need the first one to be negative. If I start with k equal 1 and I raise it to the kth power, that will guarantee the first one is negative, and then it will be negative, positive, negative, positive. It looks like this is a formula that will generate that Taylor series centered at pi. The next question, of course, would be, where does it converge? If we were to do this, we would again use the ratio test. You may want to pause the video here, go compute the ratio test on your own, then turn it back on to see if you got the same interval and radius of convergence that I got. Now that you're back, let's see if you got what I got. I applied the ratio test to the sequence formed inside of the infinite series. And again, this is a series that's going to infinity. I can ignore the alternating part, the negative 1 to the k, but not anything else. I wrote it with a sub k plus 1 as the first fraction, and the reciprocal of a sub k as the second. I replaced the k's in the first one with k plus 1, then multiplied out the arithmetic above it in a different color. That gave me 2k plus 1 factorial in the denominator, and 2k plus 1 is the power on x minus pi in the numerator. The next line down, I combine together my x minus pi's raised to a power. Again, since the base in both cases is x minus pi, I can subtract the powers. The numerator power was 2k plus 1, and the denominator power was 2k minus 1. Again, I worked out the arithmetic in a different color to get 2. I also took the factorial 2k plus 1 and stretched it out and expanded it to become 2k plus 1, subtracting 1 to get 2k, subtracting one more to get 2k minus 1 factorial. That allowed it to cancel with the 2k minus 1 quantity factorial that I had in the numerator. The next step was to clean up the algebra a little more. Notice that I have x minus pi raised to the second power, none of which depends on k. That means I can pull it out of the limit, and I don't need to keep the absolute values because it is squared. That leaves 1 over 2k times the quantity k plus 1 in the denominator, which definitely goes to 0. Since 0 times any constant is 0, this tells me that it will converge no matter what x value I choose, so that the radius of convergence is infinity and the interval of convergence is negative infinity to infinity. Let's look at example 7, find the Maclaurin series for the function e to the x. We looked at e to the x yesterday when we were looking at Taylor and Maclaurin polynomials. E to the x is kind of a fun one for the simple reason that the derivative of e to the x is always, you've got it, e to the x. That makes it much easier to compute. So now when we do the derivative, all the derivatives, of course, are going to stay e to the x. I can simply go ahead and write them in. I don't need to compute them. I know all derivatives are e to the x. I'm not sure what's happening here with my values, so we'll ignore that for the moment and hope that the next time they open up correctly. Now, are we looking for a Taylor series or Maclaurin? This says Maclaurin, so that means the center, A, is 0. When I plug in the value of the series, since it's a Maclaurin series, A must be 0. And that will give me, of course, e to the 0, which is going to be 1 for every single one of these values. This makes it much easier to work with e to the x when it's centered at 0, and it has no factor being multiplied by the variable x. If it did, we would have to use chain rule and we would end up with some more numbers at the front, but it still wouldn't be terribly difficult. Let's go ahead and write down, if we can, the pattern that we see developing. Remember that our terms have to follow c sub 0, x minus the center, but of course our center is 0 to the 0, which means ours will all be multiples of just x. c1 x to the 1 plus c2 x squared plus c3 x cubed plus c4 x to the 4th, and so on. That should be more than enough to find the pattern. Remember that c sub 0 is the 0th derivative of the function at the center divided by 0 factorial. In this case, all of our derivatives at the center are 1. So 1 divided by 0 factorial, by definition, is 1. This gives me that, and x minus 0 is x to the 0th power is 1. So that gives me 1 for my first term. My second term is going to be c1, which again the numerator will be 1, but it will be divided by 1 factorial, which is still 1, but multiplied by x, so I get x. And perhaps I should move at least this part to the next page so that I have enough room to keep writing. All right, so on the next page, I've got 1 plus x. The next term, of course, was my c2x squared. c2, the second derivative at 0 is still 1, but now it's divided by 2 factorial. So I have 1 divided by 2 factorial x squared. c3, the numerator is still 1, but it'll be divided by 3 factorial times x cubed. c4, the numerator will be the 4th derivative at 0, which is still 1, but divided by 4 factorial and multiplied by x to the 4th. This is more than I need to see the pattern developing. In this case, I find the 3rd, 4th, and 5th terms more helpful to develop the infinite series formula. When I'm looking at them, if I want to start, you'll notice that the powers of x are 4, 3, 2, that's 1, that might be 0. In that case, let's see if we should maybe start when k is 0. If we start with k is 0, then I would take x, raise it to the k power. That would work to generate 4, 3, 2, 1, and no x, because x to the 0 is the number 1. The numerators are always 1, but the denominators, notice that they match the powers on the x, so I must have a 1 over k factorial. You may wonder, well, does that work for x? Yes, it does. 1 over 1 factorial is 1x to the first. Does it work for the first term? If k is 0, 0 factorial by definition is 1. So 1 over 1 gives me 1. X to the 0 is also 1, so I do get 1. That means that my formula can be written as one combined fraction as the infinite series from k equals 0 to infinity of x to the kth power divided by k factorial. Now we need to know, where does this converge? What's the radius and interval of convergence? It is impossible to get the k factorial inside the base of the exponential, and it does depend on the index of summation. That means my only choice is to use the ratio or root test. With a factorial, it's almost always going to be the ratio test. Let's create a little more space and look for our radius and interval of convergence. To find the radius and interval of convergence, we want to apply the ratio test. To apply the ratio test, remember that you need to take the absolute value of the ratio of the k plus first term over the kth term, with the limit as k is going to infinity. All of that must be inside absolute values. X to a power, which I will replace with k plus 1, over the k, which I will replace with k plus 1 factorial. Replacing k with k plus 1 for the numerator leads to this first fraction. To get the a sub k term in here, I can simply multiply by the reciprocal, which is the reciprocal of the original. That gives me k factorial over x to the k. Again, this is a sub k plus 1 times 1 over a sub k. Because a sub k is a fraction, multiplying by 1 over a sub k is multiplying by the reciprocal, which is what I have here. Now I need to expand the x to the k plus 1 so that I can write part of it as x to the k, and expand the k plus 1 quantity factorial so I can write part of it as k factorial. To make it easier to see what cancels, I'll write these directly above one another. This is giving me the value of rho from the ratio test. For the ratio test to converge, I need rho to be 0 or less than 1. This will give me x times x to the k. Since the bases are both x, I add the powers. 1 plus k gives me back k plus 1. In the denominator, I'm going to put underneath the x sub k, since these come from the same part of the original sequence. For the next part, I'm going to put the k plus 1 in the denominator by writing k plus 1 times k factorial. In the numerator, I still have a k factorial. That makes the k factorials common, so I can cancel those out. I also have a common factor of x to the kth power, so those cancel. That leaves me a monomial x by itself in the numerator and a binomial factor k plus 1 in the denominator. X by itself does not depend on k, so I can take this x and factor it out of the limit. However, because the power on x is odd, I need to make sure that I put it in absolute values. Thus, rho becomes the absolute value of x times the limit as k goes to infinity of the absolute value of 1 over k plus 1. 1 over k plus 1 definitely goes to 0 as k goes to infinity. So again, I find that I have the absolute value of x times 0, which will be 0 for any finite value of x. Since x has to be chosen before I can plug it into the power series, x is always a finite constant. This again means that the radius and interval of convergence are everything. The radius of convergence is infinity, and the interval of convergence will be from negative infinity to positive infinity. Let's look at the last example for this part of the course. In example 8, we are again looking at e to the x, but centered at -1. This will not change the derivatives, which will stay e to the x. However, it will change the value that we get when we plug the center into the function. This means that this column is still all e to the x's. In the next step, I want to plug those values or plug the center into each of those derivatives. Since the derivative of e to the x is e to the x forever and ever, I need the value of the center to plug in. The center this time is -1. It is a Taylor series, so named because it does not have 0 for the center. Otherwise, we call it a Maclaurin series. And again, these were named for the British mathematicians who studied these extensively in the 1800s. So since my center value A is -1, this will give me e to the -1, which is 1 over e. That means that all of these become 1 over e. And I can't seem to get this to stay still. Stop moving. 1 over e, which is 1 over e, 1 over e, 1 over e, forever and ever. Let's now write down what we believe the infinite series formula would look like. Remember that we will have C0 times x minus the center, but the center is a -1. That's going to give us a double negative there. Since it's a double negative, that will make it a plus. So from now on, I'll write it as x plus 1, but it was, of course, actually minus a negative. Let's see if this is enough to find the pattern. C sub 0 is going to be the 0th derivative with the center plugged in, which is 1 over e over 0 factorial times x minus a -1 to the 0th power. The binomial to the 0th power becomes 1, and by definition, the 0 factorial is also 1. That gives me 1 over e for my first term. In the next one, C1, the first derivative at the center is also 1 over e, and it's divided by 1 factorial. 1 factorial is also 1, so I get 1 over e, but it is also multiplied by x plus 1 to the first. The second constant coefficient will be the second derivative at the center, which is also 1 over e, but it is now divided by 2 factorial and multiplied by x plus 1 quantity squared. You may want to leave it in this form even though it is a complex fraction, because it may make it more clear what the pattern is as we develop it. If I were to go one more, I would again have 1 over e for the third derivative at the center, divided by 3 factorial x plus 1 quantity cubed. And of course, the pattern continues indefinitely to infinity. Now let's see if we can write down a formula for this pattern. Uh-oh, I'm out of page. Yipes! Okay. And of course, it's going to delete all of that. Okay. So let's see if I can get it to go back up to the top. I may have to fix this later. We'll see if I can get it to go or not. Oh, yay. Okay. All right. So I kind of ran out of space here. Clearly, I did not allow enough pages. Okay, so we'll add in a couple of pages. Continuing on, let's find the formula for the infinite series. I don't know where I want to start, so I'll start and leave that blank, but I'll go to infinity. It looks like the pattern, we definitely have an x plus 1 raised to a power. If I let the power be k, then I would need to start k at 3, 2, 1, 0. So k would need to start at 0 to make that power be k. If that's a k, then I'm also going to be dividing by 3 factorial, 2 factorial, 1 factorial, 0 factorial. So I will also have this divided by k factorial. What about the 1 over e? If you look at this, you can tell that the 1 over e is in fact never changing. It's just a constant being multiplied by every term. You could, if you wanted, put the e in the denominator as a 1 over e, or instead, you could also put the 1 over e outside of the sum, since it does not depend on the index of summation k. And then you could write the formula in this format here. Now, in order to determine whether, or rather where, it's going to converge, we would again need to either write it as a geometric series with everything inside parentheses and the kth power outside, or apply the ratio test. Because of the k factorial, I can't get everything in parentheses, so I'm going to apply the ratio test. Here's the ratio test. You may want to pause the video here, compute the ratio test on your own, and turn it back on to see if they match. Hopefully you tried the ratio test on your own. Notice I did include the 1 over e, though that's not strictly necessary. This represents a sub k plus 1, and this represents the reciprocal of a sub k, 1 over a sub k. I stretched out the x plus 1 to the k plus 1 by subtracting the two powers, k plus 1 minus k, which gave me x plus 1 to the first. I expanded the k plus 1 factorial into k plus 1 times k factorial, which then canceled with the k factorial in the numerator. Since the x plus 1 no longer depends on k, I can factor it out of the limit. Because it has an odd power, I have to include it in the absolute values. This left the limit of 1 over k plus 1, which goes to 0. Thus, the limit is 0. Because this means it converges no matter what the x value is, it will converge for all x. So the radius of convergence is infinity, and the interval of convergence is negative infinity to infinity. Now, I don't want to give the impression that all of these are going to result in a radius and interval of convergence being everything. They certainly do not. However, I chose to use functions that converge for everything to demonstrate to you the power of using a Taylor or Maclaurin series. We can use these series to approximate exponentials and sines anywhere we want, and we will get the precise answer. Or if we use a Taylor or Maclaurin polynomial, we can get the answer to any degree of accuracy we desire. This is the end of this particular video on Taylor and Maclaurin series. In the final video, which will be much shorter, we will deal with the remainder for a Taylor and Maclaurin polynomial and the remainder for a Taylor and Maclaurin series, and talk about how you can apply the remainder to find out how far off you are when you use a Taylor or Maclaurin polynomial to approximate the series.